Okay, good afternoon, everyone. This is our lecture 10. Today, we're going to continue our discussion on the model-based clustering or the missing data problem in general. So the model-based clustering means that we use a probabilistic model to describe our data. And we are going to do the clustering via fitting the model or via estimating the model parameters. So in general, these model-based clustering will involve two sets of random variables. One is the xi to represent our ith data point. The other is zi for the hidden membership. Let's say we want to cluster our data into k clusters, which we wrote right here, into k clusters. We basically assume the hidden variable, membership variable for point I, to be following a multinomial distribution with 1 as the total, which means we're going to draw ones, and we'll draw 1 from k categories. And the k categories correspond to the k components or k clusters will have probabilities p1 to pk, which sum up to 1. So this multinomial means that whenever I sample ones, I will get one of the k's, 1 to k. And given each zi being in one cluster, k, I will sample the data point I can observe from a Gaussian distribution with its mean and its variance. So this is what we call a Gaussian mixture model. So the goal is to use our observed data, one per each xi. So I have x1 to xn observed, and we're going to decide what will be our guess for zi. Okay, so we'll guess the zi based on this what called posterior probability. That is, we will compute what is the probability for zi being k, given that we observed xi being lowercase xi. And we're going to use the Bayes formula to do that. And so in the end, each data point I will have capital K probabilities as Q1 to Qk, which means that we will have a posterior probability for each cluster K. And we will pick the cluster whose Qk is the largest, and we will assign the data point I to that cluster. That's the whole idea. But the challenge here is how can we estimate the model parameters? If we cannot do that, then we will not be able to compute this QK because PK is a parameter and each FK involves two parameters, the mu K and sigma K squared. We can only compute this when we know those parameter values, but we don't. Then we need to estimate those parameter values from our data. So that amounts to a parameter estimation problem, or we say it's a model fitting problem. So to give you a concrete example for this missing data problem, not in the Gaussian mixture model case, but in a more, or I would say easier case for just binary data. So we have binary indicator, binary zi, and binary xi. So let's talk about that first. And hopefully you will be able to generalize this to the Gaussian mixture model in your homework. So what we do is that we consider the I data point I is for the ith respondents. So we are in a social science setting. So we have n respondents. So that will give us data point I from 1 to n. For the ith respondent, we will have its response, or you can consider this to be a vote, and it's a binary vote, and 0 or 1. So probably you can say this is a vote or answer to a question. We can use 0 to represent no, 1 to represent yes. But there's a hidden variable we don't know. That is the political attitude of this ith respondent. So we can encode the attitude as liberal or conservative. So that can also be put as a binary coding. So we can call the liberal as 0 and 1 as conservative. Okay, So then we are going to infer whether this person is a conservative person or is a liberal person based on these xi's. So that's the simple problem we're going to tackle here. Xi's are observed and zi's are hidden. So suppose that you don't know anything about this model-based clustering. What will be your assignment? You will probably think, okay, if I know the people who answer this question as 0 are more likely liberal, and the people who answer this question as yes or 1 are more likely conservative, then I will just put all the xi equal to 0 people as liberal, put all the people with answer 1 as conservative. That's what you will do intuitively. But we're actually going to use this to give you a more model-based way so that you can see we can probably actually add our prior into the problem. That is, we know, okay, if we can assume what is how likely is a liberal person going to answer no? How likely is a conservative person to answer no? So if we can add that, probably we can do something a little more different. But just let's put this problem aside first. Let's try to think of it. What a probability model can we write for this data? So clearly, each zi as a binary variable, they should follow a Bernoulli distribution. Okay, so now let's write down the model. For zi, it's natural to assume that they are IID, all independent, following the same Bernoulli with parameter gamma. So gamma here means that the probability zi equals 1. And in our definition, it means that it's the probability that a person or a respondent is conservative. This is what we have for a population. What is the percentage of conservative people in our population? And then we are going to draw our xi given the zi. So just as we did what we did for Gaussian mixture model. So given zi equals 0, I'm interested in how likely this person is to vote yes. So again, this is a Bernoulli variable, right? Xi can only take two values, 0 and 1. So we're going to give this a parameter Bernoulli theta 0. So theta 0 means that if a person is liberal, how likely this person is going to vote yes. And similarly, we're going to have xi equals 1 given zi equals 1 to follow another Bernoulli with parameter theta 1. So here now we have 3 parameters, gamma, theta 0, and theta 1 in our model. And we're going to estimate those parameters so that we can assign a person to liberal or conservative based on its xi, just as what we did for the posterior probability here. Okay, so what do? So to start with, we can think of the simple case when we already know xi and zi for each person. So let's assume that zi's are now observable instead of being unknown. How do we estimate the 3 parameters, gamma, theta 0, and theta 1? Gamma, theta 0, and theta 1. That's our question. And we are going to use the maximum likelihood estimation approach. So to do that, maximum likelihood estimation. To do that, we need to write down the likelihood. So when we assume there are no missing data, that is, the Z1 to Zn are observed instead of missing. Okay, we can write down what we call the complete likelihood. So as I said before, the likelihood is a function of our parameters, gamma, theta 0, and theta 1. So when we are under the complete likelihood, we can use all the data to define the likelihood. So here they will be given x. I use the semicolon to mean it's given our data x and z. So let me just give you this notation. I write x as our vector of observations of the votes. I put x1 to xn into a vector. Okay, usually you will see people write this transpose because in many mathematical books, we assume a vector is a column vector. So therefore, if you write it in the row, you put a transpose here to mean that, okay, it's actually a column vector. And also for z, we put z1 to zn into a vector and call that z. Then when we write down the likelihood, complete likelihood, it's defined as the joint density. It's as a joint probability because they are discrete here of x and z given the parameters theta, gamma, theta 0, and theta 1. Okay, so now we assume that given this independence, we are going to write this joint density as a product of our observations. So we're going to write product I goes from 1 to n. So then it will be the probability, okay, that xi is equal to our observed data, lowercase xi, 0 or 1. And zi is equal to our observed zi, lowercase zi, but we actually cannot observe it. We are just assume that we can observe it to make it simpler, given gamma, theta 0, and theta 1. Okay, and then we can further decompose this joint probability into the conditional probability of xi given zi times the probability of zi. Okay, so we do one more factorization. We have the probability xi equals xi conditionally on zi equals zi. And of course, we still have the gamma, theta 0, theta 1 involved here times the marginal probability of zi equals lowercase zi given the parameters. Please note that we don't need to always write out the parameters. So these are optional and you don't have to write them out, okay? But it's sometimes easier to write it out in case during the parameter estimation, we're updating these values. So when we do that, it's better to write out the current value you calculate your probability based on. So when the values are changing, it's better to write them out, but you don't always have to. Okay, so for this part, the first part, what's the value? So this will actually depend on what the zi's are, right? We can consider the 4 possibilities. If the lowercase zi equals 0, then this xi will follow Bernoulli theta I, what we have here. Then we're going to write down this probability in terms of Bernoulli theta I depending on the value of small xi. If the small xi is 0, the probability will be 1 minus theta 1. If the small x is 1, the probability will be theta 1. So that's one case when zi equals 0, when zi equals 1. When zi equals 0, then if xi equals 0, we will have the probability 1 equal to 1 minus theta 0. When xi equals 1, we'll have the probability theta 0. So therefore, we can actually unify what I just said into this form. So let's take a look. So I can write this first part as theta 0 to the power lowercase xi times 1 minus theta 0 to the power 1 minus xi. And together, I give this a power 1 minus zi. Okay, and continue. I can put theta 1 to the power xi times 1 minus theta 1 to the power 1 minus xi together to the power zi. You see, by putting them together, I just implement what I said. When zi equals 1, when xi equals 1, I get theta 1. When zi equals 1, xi equals 0, I get 1 minus theta 1. The reason I can achieve this is because zi is binary. So I'm either at here or at here. And also, xi is binary. So given zi, I'm either at here or at here. So I will only pick one of the four probabilities depending on my value of xi and my value of zi. So this is something we use to write down the probability mass function of a Bernoulli variable, if you are familiar with that, right? If we only have one, so that's the case for the last part. For this zi takes value zi, for this probability, that's the Bernoulli mass function. It's either gamma when zi equals 1 or 1 minus gamma when zi equals 0. So the last part is just the Bernoulli mass function. But for the previous parts, we consider zi and xi. Okay, do we have questions about this part? Okay, so that's our likelihood. That's exactly what our likelihood is. And then to find the parameter values for gamma, theta 0, and theta 1, to maximize this complete likelihood, our usual approach is to take a log of the likelihood and call that log likelihood. The reason for doing so is that we can change the product to sum and we can move the power down as multipliers. So that can make things a lot easier for us. So I'll just write that down directly. So after take the log complete, I'll call that complete log likelihood. Okay. For the complete log likelihood, I can write down this directly. Gamma, theta 0, theta 1, given the complete data x and z, right? And I'll change product to summation, right, from 1 to n. And then I'm going to have this form will give me, okay, I'm going to have 1 minus zi, okay, times xi log theta 0 plus 1 minus xi log 1 minus theta 0. That's for the first term. The second term, I get the plus zi, and I have log, xi log theta 1 plus 1 minus xi log 1 minus theta 1. Okay, and I'm not done yet. I have another term to deal with. So I just write here, and what's remaining is that plus zi log gamma plus 1 minus zi log 1 minus gamma. And that completes the sum. So then what I'm going to do is that I'm going to find the maximizer of this log likelihood. And the approach I'm going to take is to take the partial derivative of this log likelihood against gamma, against theta 0, against theta 1. So I'm going to have three equations. And I'll set all of them to 0 to find the root. And that will be the maximizer. Gamma hat, theta 0 hat, theta 1 hat, which we call the MLE. Okay, so here we are going to just do that differentiation directly. So we are going to do partial L, partial gamma, and that will be set to 0. Okay, and also partial L, partial theta 0, set that to 0, and partial L, partial theta 1, set that to 0. And we can actually solve it and then found that the 3 MLE estimates based on complete log likelihood will be, we call that gamma hat MLE is just equal to 1 over n summation Zi. That is the proportion of respondents who are actually conservative, because Zi equals 1 being conservative. That's the proportion of conservative people in our sample. We use that to estimate gamma. And we have theta 0 hat MLE, which can be shown to be just summation. This is for I as well, I from 1 to m, 1 minus Zi times xi, divided by the summation I from 1 to m, 1 minus Zi. That's the MLE for theta 0. And finally, the MLE for theta 1. It will be summation I from 1 to n, Zi xi, divided by the sum of Zi. So how do we interpret those 3 estimates? The first one is obvious. The second one is that when I take the summation of 1 minus Zi, essentially I'm only counting the people whose Zi is 0, right? The people who are liberal. And among the liberal people, I count how many of them voted yes for xi. So that's why this is the proportion of voting yes among the liberal people. And that's our definition of theta 0 in the population. And we're estimating that from our sample. So it makes sense. And for theta 1 hat, I'm counting the people whose Zi is 1, which means they're conservative. Among those conservative people in my sample, I counted what proportion of them are voted yes. So that's also agreeing with the definition of theta 1. So the only difference is that theta 0, theta 1, gamma are population parameters, while here I'm computing estimates from my sample. So complete likelihood seems very straightforward, right? We can do that after you take the 100B class, I would say. But now the issue is that we are missing, we are under the missing data scenario. So under the missing data scenario, we cannot write the complete likelihood like this because we don't know Z. Okay, so when Z is missing, the complete likelihood is unavailable. Then what's the likelihood? The likelihood is only based on the data we observe. So the likelihood is actually, we can write it as likelihood of gamma, theta 0, theta 1, only given our data x. And by the definition of likelihood, it's the joint density, or here's joint probability of x given the parameter values. How do we write this out? So given we have this, how do we go from the joint probability of x and z to the probability of x only? Can someone tell me the answer? How do we go from the joint probability of x and z to the probability of x?
Integration?
Integration, right? Integration is the correct answer. And here specifically, because z is just binary, right? Each xi is binary, we would just do summation. So in other words, we will just enumerate all the possible values of z1 to zn, take the sum, and then that will give us this, we call marginal probability for x only. This is what we did, if you recall, when we talked about that empirical Bayes estimate for the variance in the two-sample t-test problem. We actually did this. We said that if you have a prior probability distribution that involves some unknown parameters, you want to estimate those prior parameters from data. What we do is that we actually write down the joint likelihood of the prior parameters and our parameter of interest, the sigma square, that thing together give our data. Then we integrate out the sigma part, sigma square, and we are only left with the prior parameters with our data. And then we maximize that prior parameters likelihood to estimate the prior parameters. We call those empirical Bayes estimates, and then we put those back in to do our Bayesian inference. That's what we did before. And here, it's very similar. We need to integrate the thing we don't have information for. That's Z. So essentially, this is just this. For each Zi, we consider its two possibilities, either 0 or 1, 2Zm. Either 0 or 1. And for each possible values of Zi, what we do, Z1, this should be, what we do is that we compute the probability of this. X, of course, is equal to what we observe, right? Xi equals to x1, blah, 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 2xm equals our observed xm. These are our observed data. Then Zi equals to the Z1 to the possible value Z1 to Zn equals the possible value Zn given gamma theta 0, theta 1. And the computation of this is the same as we had before. So still this one. But what we have here is, so I can just write one more step so it's clearer for you. So Z1 equals 0 or 1. Summation to Zn equals 0 or 1. And we have this product again for the independence, I from 1 to m. Then we have the probability xi equals lowercase xi given zi equals lowercase zi. Okay, I'm leaving out the parameter here just for simplicity, times the probability zi equals zi. So what I'm going to have is the same as here, but I have those summation, n summations before. So you can see how many possibilities I have here. It's actually 2 to the n, because each zi has two values and I have n of such zi's. So, and this step, this procedure is something we call marginalization, which means we can go from a joint probability to a marginal probability. So if you can write down this, which we can actually do, right? Given this formula, this thing we have here, we just need to take a summation for each zi being 0 or 1. If we can do that using our computer, then finally, we just want to find the values of gamma, theta 0, theta 1 to maximize this function of theta 0, theta 1, and gamma. That's what we need. So we call this approach the brute force approach. That is, we directly use our computer to do the marginalization and then do the maximization. Do we have a question about this? So you can imagine that if your Zn is very small, it's probably doable. Even though when we don't have a computer, this is also very expensive, computation expensive, but now it's doable. But you can imagine if your n goes larger and larger, you'll have so many summations to be taken for. So that's definitely not something computationally efficient. So the EM algorithm, which stands for expectation maximization, was proposed to address this problem. So instead of using the brute force approach to maximize the likelihood based on our available observed data, we want to utilize the complete likelihood to help us make this optimization problem easier. Because we see if we have the complete likelihood, the maximizing it to get MLE, it's computationally very simple. We just need to compute those three formula, we're done, right? So we hope we can use this in our optimization for the likelihood in some smart way. So next thing I'm going to introduce is the EM algorithm. So this one is computationally intensive. So a smarter solution, I would call this a smart solution, is the expectation maximization algorithm. It's a very important technique invented in the statistics community in the 1970s, and it has been so popular since then. So it uses a very smart idea for maximizing the likelihood based on the complete likelihood. But don't forget that here our goal is still to maximize the likelihood, this one, okay? This is still our objective to be maximized, not the complete likelihood, because that one is not available to us and it's not meaningful to us because we don't have Z. But to achieve the maximization for likelihood, we could use the complete likelihood to help us in a middle step. So the goal is to maximize this gamma theta 0 theta 1 given Z. Okay, the same goal for MLE. So what do we do? Let me introduce what we do in the EM algorithm first, then we'll try to justify why it will work. So by the name, this algorithm as an iterative algorithm will have two steps, expectation step and maximization step. So in short, for the expectation step, what we try to do is that we try to find an expectation of our likelihood or log likelihood, like log likelihood in terms of, I would say this, find the expectation of our log likelihood with respect to the missing variable Z. We are going to do that, and that can give us what's the expectation given the data X, given the current parameter values gamma, sigma 0, sigma 1. So once we obtain that expectation, we're going to use that expectation we're going to maximize that expectation to update our parameter values in the maximization step. And then given the current parameter values, we're going to calculate our expectation of the complete likelihood with respect to Z again. And then given that new expectation, we're going to maximize that expectation again to update the parameter values. So we're going to do that iteratively until convergence, until our parameter values no longer change. And so in this special case, when we apply it to our problem here, okay, in our special case, we can show that the E step can be reduced to calculating the expectation of Z, this hidden variable or Zi, given current parameter values. So I'm going to write that down. And I want to emphasize this is the special case. We are going to talk about the general case later. So in the E step, you can consider it by intuition as some sort of imputation. We are going to impute the missing values missing data based on our observed data and current parameter values. So let's assume here we already have our parameter values. I call them theta for gamma t, theta 0 t, and theta 1 t. So this is some value we have obtained already. So we are in the process of doing iteration. We want to know what will be the expectation of Z. So we are going to calculate the expectation of Zi given my observed data, given the current, I can write in this first, given the current parameter values, gamma t, theta 0 t, and theta 1 t. Okay, I need this. And once I can compute this, it's as if I have access to the hidden data. Then in the next step, I'm going to use this expectation in place of the Z1 to Zn in my complete likelihood. Then I can use the complete likelihood MLE directly. So this is a very easy computation. So how do we compute this? So the first thing we need to know in our special case, of course, the zi is a Bernoulli variable. So for Bernoulli variable, its expectation is just equal to the probability that it takes value 1. So it's equal to the probability zi takes value 1 given our observed data x, gamma t, theta 0t, and theta 1t. Okay, that's what we need. And to compute this, again, we're going to use the Bayes formula. Bayes formula is always the easy thing for us to swap what's before the conditioning and what's after the conditioning. So what's after the conditioning and being random is the xi. And what's before the conditioning and being random is zi. So therefore, I can write this just as this. So I'm going in the numerator, I'm going to have this probability of xi given my observed data xi, right? Times, so I can just say that probably I can just write 2 steps for your reference. Zi takes value 1 given the current parameter values, gamma t, theta 0t, and theta 1t. This is the joint probability. I'm going to divide this by the marginal probability of xi. Xi equals this, gamma t, theta 0t, and theta 1t. Okay, this is the Bayes formula. And furthermore, I'm going to write the denominator as the summation of the joint probabilities of with zi equals 1 and zi equals 0. I'm going to have 2 terms. And for each joint probability, I'm going to write it as xi given zi times the marginal of zi. So that's just based on my model, right? I have zi first, zi being generated from Bernoulli first, then I generate my xi given zi. So that's just easier for me to write it out. So essentially, I'll just go one more step. So I'm going to write this as the probability xi equals xi given zi equals 1, okay? And the parameters. For the new denominator, I need to consider 2 cases. I'm sorry, not done yet. The probability zi equals 1. For the denominator, I need to consider zi being 1 or zi being 0. So I'm going to write a sum. So then you can see this zi, lowercase zi equals 0 or 1. I consider 2 cases. And then I'm going to write this xi, zi equals this parameters times the probability big zi equals small zi parameters. Okay, so we can use whatever we have from the likelihood, the complete likelihood, or the generated model for this. We know, okay, when zi equals 1, use our current parameters to write it out. So when zi equals 1, what is the probability for xi takes small xi value? It's depending on what the small xi is, right? So by the same argument, it's either theta 1t, don't forget we're using this current value, to the power xi when it's 1, or 1 minus theta 1t to the power 1 minus xi. This is what we have for this probability. For the second part, zi equals 1, right? That's the probability we have. So we know it's just gamma. It's just gamma t. And for the denominator, we need to consider zi being 0 or being 1. So we'll have 2 terms. So it's actually theta 1t to the power xi times 1 minus theta 1t to the power 1 minus xi times gamma t. That's the case when zi equals 1. Plus when zi equals 0, I have theta 0t to the power xi times 1 minus theta 0t to the power 1 minus xi times 1 minus gamma t. This is for z equals 0. So using this formula, you see, what we have is using our observed data xi and using our current values gamma t, theta 0t, and theta 1t, we are going to find the current expectation for each zi. So we are going to impute it using this formula. That's what we call expectation step for our hidden or missing data. Then in the maximization step, or we call the M step, what we're going to do is basically the MLE of complete likelihood, what we have seen before, except that we are not going to use our Z as observed because we don't. We are just going to use the imputed Z from the E step in that complete likelihood. So in other words, we are going to maximize, or we're going to update parameter values as, I'll call them as gamma t plus 1 for the next set of values, theta 0 t plus 1 and theta 1 t plus 1 as the maximizer. Okay, I'll say I'm maximizing for theta, gamma, theta 0, theta 1 for the maximizer of the complete log likelihood of gamma, theta 0, theta 1, given, of course, z, right? And also something here, I'm going to give this a notation. So I'm going to give this a notation. I will call this tau it. Okay, so tau it is the expectation of zi in the tth iteration, given the current values, parameter values in the tth iteration. So I'll call this tau it. So basically, if I stack them together, then I will have a tau t, okay? So tau t is just a vector that contains tau 1t to tau nt. Just as we have x1 to xn to be called x, z1 to zn to be called z, we call tau 1t to tau nt to tau t. So therefore, we're going to write the complete log likelihood, but with the data as x and tau t. So our expectation from the E step. Then we use the formula here. So then you can see whenever we write zi here, we're going to write tau it here for the update. So in short, we're going to have, let me get another piece of paper. So we're going to have gamma t plus 1, just as 1 over n summation I from 1 to n tau it. I'm going to update in this way. And for theta 0 t plus 1, I'm going to update it as summation, not for 1 minus zi, but 1 minus zi tau it in the denominator. In the numerator, I have 1 minus tau it times xi. That's for theta 0. And for theta 1, I'm going to update it similarly. In the denominator, I have summation for tau it. In the numerator, I have the summation for tau it times xi. So you see, I get my next set of values for gamma, theta 0, theta 1. Then I'm going back to the E step. I'm going to go back to the E step and then use the same formula, except that I'm going to use theta 1 t plus 1, gamma t plus 1 and theta 0 t plus 1, then I will get my tau I t plus 1. Then with my tau I t plus 1, I come back to here to the M step to get my gamma t plus 2, theta 2 t plus 2, theta 1 t plus 2. So that's how the iteration goes. And then I can do this continuously until my gamma, theta 0, theta 1 values no longer change. So I stop. That's the EM algorithm for this special case. So you see that we don't need this brute force calculation to take over a sum for 2 to the power n terms, right? That's tremendous. We don't need to do that. We just need to do this iteration. And if your initial values, gamma, theta 0, theta 1, are set to be very close to the MLEs, we can actually have a very fast convergence. So in other words, we're still having the same objective function as the brute force to maximize the likelihood for based on x only, but we can utilize the complete likelihood and its closed form, nice MLE formula for our maximization step. So that can give us a very easy computation for the maximization step. We just need to get expectation updated as we update our parameter values. So does this make sense to you, or how the algorithm works? Is it clear? Okay, so yeah, so I just did a demonstration for this problem, and for your homework, you're going to do the derivation yourself for the Gaussian mixture model. So my hint for you is that you're also going to start with a complete likelihood. So when you have both xi and zi, you're going to derive the formula. For the Gaussian mixture model, you will have a gamma there for the zi's success probability. You're going to have mu0, mu1 for the two means of the two Gaussian components. And you're going to have sigma 0 square, sigma 1 square for the two variance parameters of the two Gaussian components. So you need to get 5 MLEs here. This will be used as your update formula in the M step. And in the E step, you're going to calculate expectation of Zi given the X and given the 5 parameters. So still it's the same base formula, but what's different here is that this is the same. Zi equals 1 is the same, but what's different is the distribution of Xi. Over there, you are going to use the Gaussian probability density instead of this Bernoulli density, Bernoulli mass function. So that's the thing you need to be clear about. But other than that, it's basically the same idea. So the only difference is given Zi, the distribution of Xi is different. Here, the distribution of Xi given Zi is just Bernoulli, but in your homework, it's a Gaussian or normal distribution. Okay, do we have questions before we move on to talk about why EM algorithm works, right? Why does this approach maximize the likelihood? That's the next topic.
Professor, I just kind of want to ask, is this also the algorithm that we went over for k-means?
For k-means?
Yeah.
Oh no! Actually, you have raised a very good question. So there is a theoretical paper that basically says, okay, k-means can be regarded as a kind of EM-like algorithm. Yeah, so it's like when you do so for k-means, what's similar is that when you do the assignment, when you assign each data point to a cluster, it's kind of like the E step. And when you use the assigned points to update the cluster centers, it's kind of like the M step. But what in the k-means algorithm, there is no probability distribution, there is no likelihood, there is no expectation. We don't use those concepts at all. It's purely an algorithm. But if you think of the EM algorithm by assuming your data is following some distribution, so that basically solving the E step and the M step can be considered as the corresponding assignment step and the center calculation step, yeah, then you can find that correspondence. There's an analogy, but not exactly the same. Just to emphasize that k-means doesn't rely on any probability distributions. Okay. Yeah, that's a very good insight. Okay, so then let's continue. Why the EM algorithm works. So to really understand this question, we need to first give you a math review on what we mean by a convex function and a concave function. Okay, so by convex function and concave function, so they are, if you understand the two English words, you should roughly know like convex means you have a shape like this, concave you have a shape like this. That's the English definition. But in the mathematical definition, it's a little interesting that we always need to look downward to see the convexity or concavity. So by convex function, it's defined in relation to a linear function. So let's say this is our x, a function argument, and this is our fx. Okay, so convex function has this form. So what it means is that if you compare it to a linear function, if you just find any line, okay, given their two intersection points, you will always see the function lies below the linear line. If that's the case, you call this function strictly convex. So that's why I say it's looking downward. If you look from this angle, from up to down, you'll see why we call it convex, because it's going outward in that direction. And then the concave function is just defined as the negative convex function. So if a function is convex, then negative fx is concave. So when we have a function that looks like this, which means if you have a linear line that goes through it, you look at the two intersection points, and you see within the segment, the function always lies above the line. We call that concave function. So these two are very important concepts used in optimization, which is to maximize a function by finding the argument. So in the convex function, a very typical case for this is our quadratic function, like fx equals x squared. It takes this shape. For the concave function, a very famous one is the log function. If you take the log x, it looks like that shape. So one important property about the convex function is related to how do we compute the mean, okay? So let's say that I call this value as x1, and I call this value as x2. So I'm interested in these two properties or these two quantities. So correspondingly, this will be fx1, and this would be fx2. Okay, so what I'm going to compare is that for a random, or not random, I don't need to be random, for a number between 0 and 1, let me call that number as t, okay, between 0 and 1. So I'm interested in these two quantities. One is I took t times x1 plus 1 minus t times x2. What this means is that I find any point in the middle of x1 and x2. So this is like a weight t and a weight 1 minus t. So these two weights adding up to 1 will give me any point in the segment between x1 and x2. So picking a value here, let's say, I want to evaluate what's its corresponding f. So probably I can say this is tx1 plus 1 minus tx2. And then I find this corresponding f value right there. So I'm interested in this. Another thing I'm interested in is I apply the weight to fx. So what is tfx1 plus 1 minus tfx2? I'm interested in the relative magnitude of this versus this. So we can see that applying the same weight to the two fx's, I am actually getting a value bigger based on the shape, right? Because I know if I'm on the line, the linear line, then these two quantities are equal. That's how we define a linear function. So because the line is above the curve, we know this is larger than that for strict convexity. And if we are not strictly convex, at least we can say it's greater or equal than. So this is a very important property for the convex function. And for the concave function, we are just going to get the sign reversed. So this is for convex. And if it's concave, we will have it here. This is for concave F. And this blue thing is for convex F. So using this property, we can make it work for our expectation. So think of our expectation. What is the expectation of x? Let's say that if x takes two values, okay, so if fx, make it easier, if fx equals to value x1 with probability t and x equals value x2 with probability 1 minus t. If this is how my random variable x is distributed like, then I know the expectation of x is just what we have here, t times x1 plus 1 minus t times x2, right? You see in this special case. So that's why we can consider this interpolation between two values just as a can be generalized to the expectation of a random variable. So then more generally, we have this results for a convex f function. That is a function applied to the expectation of a random variable is less or equal than the expectation applied to fx. So the reason we see this is also if you look at this part, right? What's expectation of fx? By the definition of expectation, when x take only two values, x1, x2, we can still write it as at t f x1 plus 1 minus t f x2. That's why I generalize this to this. So this is a very important inequality called Jensen's inequality. So it's about swapping a function and expectation. If the function is convex, we will have the value bigger if we do expectation out of the function. Then we do expectation inside the function. So you don't need to memorize this. You just need to draw this figure yourself, and then you can figure that out. Because what you have on the curve is the function in the outside. You do expectation first, then you do function. What you have on the linear line is what you have on the right-hand side. You do the function first, and then you do expectation next. So Jensen's inequality allows us to find, you see, given these two things, using an expectation serves as an upper bound for a function on something expected. So we can take expectation to actually get an upper bound. And one on the concave, we just reverse the direction. If f is concave, we can have this for concave f. And this is what we need for our MLE, because the thing we're going to maximize is the log likelihood. And you see, we want to maximize something concave, right? So usually it's a concave function to be maximized, while it's a convex function to be minimized. So the same problem can be stated as a minimization problem or a maximization problem, depending on the sign you put. But for log likelihood function, okay, log likelihood function if concave, then it's a good maximization problem. Then we can find the global maximum for the log likelihood. Okay, so that's the case we are going to assume we are under. So we're going to assume that, okay, yes, we are going to maximize our log likelihood, which is concave. But I just want to warn you that this is just for the simple case. It's not guaranteed that the log likelihood is necessarily concave, especially when the model is complicated. So in that case, the EM algorithm can only lead us to a local maximum. Also, the gradient-based approach, like you take the derivative, set it to 0, that can also work well for one global maximum case. If you have multiple global maximum, then at each, if you have multiple local maxima, then at each maximum, you will always have the gradient equal to 0. So you have multiple values where the gradient equal to 0. That's when we do not have a unique global maximum. So the key idea of the log likelihood case for the EM algorithm is this. So you can see that basically what we have as the log likelihood. Okay, let me put it here. So it's actually log beta. Oh, sorry, I should say, I'll just make it easier for you to understand. So let's call the parameter as beta is the notation, a parameter beta. So we call that log L beta given our observed data X, right? And this is actually defined as the log function of the likelihood of beta given X. And what else? We actually can write this as the likelihood for this marginal likelihood. So we know, I'm just going to go one more step. So this is equal to the joint probability of X given beta, right? And we know that to obtain the marginal joint probability for X, we need to marginalize what to integrate our Z from the joint. So this is actually what we have if we write X, Z, beta, okay? And that marginalization involves integration. So essentially what we're doing is this, integration of Z by removing Z. So that can give us here. And furthermore, what we have is if we can actually write this term in terms of some distribution of Z. So let's see, I'm going to say assume, like I would say probably, I'll just say this. So Q, I'm trying to be a little more consistent with my notes. Yeah, so I'm going to change this to F as the joint probability density. So F, assume that we have Q, okay? QZ can be used as a density of Z, okay? If we do that, then what we can do is that we rewrite this term as log integration fxz beta divided by qz times qz dz. I didn't do anything else. I just multiply qz and divide qz, so I stay the same. But the reason I want to introduce this density, somewhat density, there could be multiple densities, right? The reason I introduce one of it is to create a form of expectation. We know that whenever we calculate expectation of random variable, it must involve a density here and some function of z to be integrated. So what we mean is that we know, just as a side note, we know that this is how we define a function. So let's say if, let's say z has density Q, okay, density function Q, then the expectation of some function of Z is defined as G, Z, Q. I should use lowercase to be more exact. Q, Z, DZ, right? This is how we define an expectation. So based on this argument and apply it here, we are going to write this part as the log of expectation of Z for Z following Q density of this term f x z beta q z. That's it. So the reason I want to specify here the expectations for Z is to mean that here I'm not considering X to be integrated out. So X will stay. What I'm going to remove is the random variable Z. And so the integration does the job. So after I solve the integration as is, after I get if I can calculate it, then Z will be go away. It would be no longer there because expectation is basically serving the role as integration. You can actually make sense of this. That is, integration is just a continuous version of summation. And expectation is a continuous version of average, right? So when you do summation, then you divide by the number, you get an average. Here, the number row is played by this density. You're going to, in the integration for every value here, you assign a density to it, and then you do the aggregation, then you get the expectation. So it's a continuous version of average. So after getting here, you see Jensen's inequality can be applied. So log is a concave f. So therefore, you can see that when it's concave and we'll use log for f, log of expectation will be greater or equal than expectation of log. Okay, so by Jensen's inequality, I'm going to have expectation of Z following Q. Moving the log inside, what would I have? I would have a log of f x z beta, because log ratio can become difference of two logs minus log qz. And then you see, I actually found a lower bound of my log likelihood. So this is a lower bound of log likelihood. I'm going to maximize. Okay, so that's the first fact we derived based on Jensen's inequality. And what's nice here is that you can recognize once I get the lower bound, inside my lower bound, this is what I called complete log likelihood. So it appears here. That is, the left-hand side is the log likelihood I want to maximize. But if I find this lower bound using Jensen's inequality, I got its complete log likelihood appearing here. So the next thing I want to introduce, this is fact one. Okay, so Jensen's inequality is the first important fact for EM algorithm. The second important fact for the EM algorithm is a very important fact for optimization. So that is this fact. Okay, so I will call this fact one. The convex function, concave function, and Jensen inequality. The fact two for optimization is this. Okay, so let me still use this graph fx. So if I'm trying to maximize a rather complicated function like this, and if I'm currently at this x value, okay, I call this x0. How can I find the next value to increase my f function value? So one possible way is that if you can find this value and you find the lower bound that's tangent with this value, tangent with this curve, then if you maximize the lower bound, so there are tangent here, if you maximize the lower bound, say call this x1. Then you can show that using this x1, fx1 will be greater than fx0. So why is that? The reason is that it's a lower bound. So first of all, because it's a lower bound, so we have fx1 greater or equal than, let me call this a g function. A g function is a lower bound, okay? So this is a g function. So fx1 is greater or equal than gx1 for sure because of the lower boundness. And then we have this x1 as a maximizer of g. So we know gx1 must be greater or equal than gx0. That's how we found x1. And then because g and f are tangent at x0, so this is equal to fx0. So you see, by this relation, we can have fx1 greater or equal than fx0. So this is a very important fact for us to do the optimization using a easy to optimize lower bound. So what we do, we require these things. Okay, so first of all, g is less or equal than fx for all the x, for any x. That's the first thing we need. And the second thing we need is that at the current value, they are tangent. So gx0 equals fx0. That's the second thing we require. The third thing we require is that g is easy to maximize. We need all those three things to implement this approach, because otherwise, if f is easy to, and f is difficult to maximize, of course, because otherwise we could just directly optimize f. Why do we need to go through this route? Difficult to maximize. Okay, so what we do is to find an easy to maximize lower bound g for f. And these two functions are tangent at the current value. So we can maximize the function g to update my value to increase my f. That's the goal. So using this idea, now we are going to consider this lower bound that involves my complete log likelihood as my g. Okay, so don't forget here the argument is beta. We're going to find the beta value for maximizing the lower bound. So in the hope that this can move up the log likelihood value for our updated beta value. So we hope that. But you see, to achieve that, we need to make sure, first, it's a lower bound. This is guaranteed already by Jensen's inequality. So this is guaranteed already. The second thing is to find the tangency. How can we make them equal at the current beta value? That's the second question to ask. We haven't addressed this yet. The third question to ask is whether this lower bound is easy to maximize itself. Okay, so we're going to stop here and we're going to come back to this next time. So I can tell you the answer as a preview. That is, to achieve the tangency, it will guide our choice of Q. Because I said that for this QZ, we have many choices for the density functions of Z, because any density can give us some expectation, and Jensen's inequality always holds, but only one choice of Q can give us equal sign at the current value of beta. All right, so let's stop here. And yeah, so for after today, you can try to solve the problem in your homework for the Gaussian mixture model, given the EM algorithm we talk about. Okay, I'll stop the recording.